Hi, in this video I'm going to show you how to generate a sinusoidal signal in FPGA using the DDS, direct digital synthesizer. Okay, for that I have the sampling frequency is f clock 100 mega. This is the frequency I want to generate. This is 2 megahertz. The phase width I will keep it 16 bits. Based on this information, according to this formula, we can grab the phase width. This formula I snipped from the DDS Xilinx IP core manual. This is the version 4.0. I will show you the formula where it is. This is the formula for frequency out. Okay, this is the clock frequency of the system, the input frequency of the DDS, and this is the phase increment, and this is the phase width. Okay, now we know how we know the other values instead of this phase increment. Uh, Phase increment value we will draw from this formula. Okay, so that if we will put these values in this formula, our phase width is 2 raised power sorry, 2 power 16 is our this value, and of f out frequency required is our 2 mega. We multiply with this value with 2 mega, 2 mega, 2 and 6 zeros. This is our multiplication of these two values, and we'll divide it to the f clock, which is 100 mega. 100 mega. This is the phase increment value, but we can put only the round of values. Okay, so I will put 1, 1, and 1. Round of this 7. Okay, 1, 3, 1, 1. This will be our phase increment value. For that, I'm going to design a project in Vivado 19.1. So now I want to create a project, and just choose the desktop. This is DDS project with DDS. Next. And if you wish, you can choose a specific board. I will just select the Z board. Here you can put the IP DDS. This is the built-in Xilinx IP. This IP has multiple options. You can find its phase as well as this data. So there are some parameters. I will keep the system clock 100 mega as for my calculation. Here's the standard size, and this is the sampling frequency. I keep 100 mega as per our calculation. And I will prefer the hardware parameters. Okay. So the phase width which we have selected the 16. Okay. And the output I will keep it 16 bit. And there is a implementation, there is multiple features. I will keep it fixed phase increment. If you will make it programmable, then you can change the frequency at real time. There will be option out from here, and you can change the phase increment in real time. So I will keep it fixed for now. The phase offset I will keep null, and this time it will generate the output of both sine and cos. So I will keep it just for sine signal. And for now, I don't need the phase output. I will just disable, and I will keep these parameters as a default. Now over here, you have to put the phase increment value. So I have to calculate this decimal value, but it need to convert it into the binary values. I have this value. The binary value I got is this one. So I will just copy and paste over here, and this is the summary. Output width is 16-bit, only one channel. System clock is 100 mega, and this is also the sampling frequency, and this is the memory and other parameters. Phase width 16-bit, phase resolution is uh, 15 1.5 kilohertz, phase width is 16-bit, all the other parameters. Okay. Now here you can see it will generate 2.0042 megahertz signals. As we had round off the value of this phase width, due to that it cannot generate exactly the value. Okay. For that you have to manage the phase value. Okay. For now I will just set the parameters. I will just make it. Okay, there is I will make port externals. I don't need this port. I will just make these two ports external. Okay. Now you can check the is there any violation or not, and you can generate the wrapper of this project. Once the wrapper is done, you can. We have only one input. You can either write the simulation testbench for this wrapper. Either you can make it uh, force value. Okay, I will just simulate it and put the force clock instead of writing the test bench of this module. I will show the test bench as well, but just to show you these features as well, I will simulate it first like this. No, we we have to put the force clock. I will keep it decimal, start from 0, trailing edge is 1, the duty cycle is 50, and for we want it to make 100 mega. For 100 megawatt, we calculate 1 divided by 100 and mega. So if we will make it in a scientific notation, it will be 10 nanosecond. 10 nanosecond is the period of this 100 mega clock. I will just make 100 mega clock and just run. Okay. Now you can see that this is the 100 mega clock signal. I will just put a marker over here. You can see it's a 10 second period of the clock signal. And if I will show you the analog of this sinusoidal signal, you can see that this is the sinusoidal signal of 2 megahertz frequency. Okay, you can put marker over here and you can calculate its sinusoidal frequency. It generates the valid signal for whole period for its generating the sinusoidal signal. Okay, the second method I will show you how you can write test bench for it. I will just select the video test bench TB of DDS. You can see how I can write test bench for this module. I have mm, I have one clock signal. Okay, then I have data which is 16 bit, and then I have a valid signal. Okay, I will just put the these features over here. This is my signals of this module. I will call this module. This is my module under the test. I will keep the uh, parameters, which is clock. Clock will call with this clock signal, and there is data, and data is replaced with data signal, and there is valid will replaced with this valid signal. Okay, now I have to generate a clock signal. I will put initial clock is equal to 0, then always 15 nanoseconds is half of the clock signal, which is equal to inverse of this clock. Okay, now you can see that our system is inside this module, this test bench. Okay, now if I will run this simulation, you cannot simulate at the same time as I have to close this one. No, I will not save the signals. No, if I will run this module, no, I don't need to put any force clock as I have designed my clock signal inside the test bench. You can see that it run for some time and there's our sinusoidal signal. If I will run for 2 milliseconds, this is what it generates the sinus signal. Okay. Please subscribe this channel. In next video, I'm going to show you how you can design a composite signals and how you can see its frequency uh, transformation. Thank you.